Good morning, everyone. Hope you all are doing good today. Today, we are going to finish up the last chapter of the textbook, which is the electrical chemistry. We got to example 4. So, for the example 4, the following reaction takes place spontaneously in the galvanic cell shown in the figure below. So we have an indication here, which is a galvanic cell. So you should know everything about galvanic cell before you even get to this example. So here's the general equation, okay, of the reaction inside the galvanic cell. And what is required from us is to write down the half redox reaction, okay, oxidation and reduction. The second thing is to indicate the direction of the electrons through the salt bridge and the direction of the ions movement through the salt bridge as well, that is filled with KNO3 potassium nitrate solution. So let's get into each one individually. So first of all, if you want to write down the redox reactions or the half redox reaction, I should know which one is or has been oxidized and which one has been reduced. So first of all, the copper right here is the anode, right? It's oxidized, or the Cu, like it was zero, the oxidation state of it, and it becomes Cu plus 2 and it released 2 electrons, right? So lost 2 electrons, okay? So it's oxidized and for the Ag, okay, it was reduced. Here are the two half reactions of the galvanic cell or of the reaction between copper and Ag, okay? This is easy, the same as you did like with the previous examples. The second thing is that we want to indicate the direction of the electrons through the salt bridge. So we have KNO3 solution. So the electron go through the external wire, okay, which is that wire, okay, and beginning from the anode, which is the Cu pole right here, okay, toward the cathode, which is the Ag pole, which right there, okay, which while the positive ions, the potassium, move through the salt bridge toward the negative pole, which is the cathode, and the negative ions NO3 goes to the toward the positive pole, which is the anode. Which means that if we have um, like a solution that can or a salt, okay, so there's like a positive and negative ions. So the ions, the positive ones, go to the where the negative ones, okay, the negative pole, okay, and while the positive one goes to the negative and the negative goes to the positive. So for here we have KNO3. K is the positive, okay, and we have NO3, which is the negative. So it's obvious that the Cu is positive and Ag is positive, so they will bind to what? To NO3, which is right here. So just like the direction, what's gonna happen inside the cell? That's it. That's all we need. Okay. So we have NO3 right here. It's simple. Now let's move to the galvanic cell potential. The pole potential is the resulting potential between the elements, okay, rod, and its ionic solution. So this one would be like explaining the potential between the element itself, okay, and the ionic solution. It could be like KNO3, for instance, as we mentioned in the previous example. So it is broken into two types, okay, the oxidation potential, the first one, and the reduction potential. The oxidational potential is the ability of a solution to lose electrons, which is obvious as we mentioned before. Losing electrons is oxidizing, and gaining electron, it is reducing or reduction. Okay. Now, electromotive force, as it's abbreviated as EMF. This is really important, especially in the final exam. It's the greatest value, this is the definition of it, of the potential difference between the anode and the cathode poles. Okay, the difference between the cathode and the anode. Okay, and it's a scale of the potential, not for the force. It's different. Be careful when you deal with EMF, the electromotive force. It's for the potential, not the force itself. So we have like a law right here, which is E cell. Okay, E cell, which is cell potential, as it's shown right here, and we had EOX. Here's the oxidation. Okay, EOX, the cell potential for the oxidation, and the cell potential for the reduction, or as it's called, the oxidation potential or reduction potential. If I want to calculate the E cell, the cell potential, I would do a summation between the oxidation potential and the reduction potential, as it is shown right here. The anode, and we have the cathode. So for the oxidation is anode, for the reduction is the cathode. Okay. At STP, standard temperature and pressure, the temperature is 25 Celsius and pressure is 1 atmosphere. The E cell, which is what? The E cell right here equal to the E anode plus E cathode. So this is the standard one. So you gotta pay attention to it. It's the same as the previous one. Okay. Standard one. Now we will be having like an example, and that example will explain what we've been talking about. To determine the standard cell potential, it's required to measure the oxidation and reduction poles potential at STP. Okay, this is the standard one, the E cell standard one, with the E standard for the anode, the E standard for the cathode. Now, standard hydrogen pole, which is one of the important things that you guys need to understand, and which is the like why we chose hydrogen pole over many others poles. There is like some, or there are some advantages that like forced us to select the hydrogen pole over, or the hydrogen as a pole over many other elements. So it was selected as a reference pole because its standard potential is known, which is 0. This is the first one, and it could be used as a cathode and anode at the same time. So for this one, I can like write down a redox reaction. Okay, for the hydrogen, one of them is by losing electrons and the other one by gaining electrons. So it acts as a reduction or reducing and oxidizing agent. Okay, and it has 0 voltage. Okay, so the standard hydrogen pole, SHP as it's abbreviated, it consists of a glass tube containing or contains hydrogen gas as bubbles at 25 Celsius and pressure 1 atmosphere, which is at STP, in a solution possesses hydrogen ion such as HCl, okay, 1 molarity, and the bottom of the tube contains a platinum piece coated with a rough layer of platinum that is connected with the wire of the platinum. The advantages of using platinum in making SHP or standard hydrogen pole is that it's an inert substance. This is really important, that does not suffer oxidation or reduction. So that's why we use platinum. So if it does act as a reducing or oxidizing agent, or if it does go through like an oxidation or reduction process, then we cannot use it. So we need to use an inert source for that. So it provides a surface to the pole that is the hydrogen molecules can dissolve or dissociate on that surface. This is the first one. The second one is that it provides a way to get an electrical accommodation with the external circuit. All right, here is like everything. By this slide, we uh, just finished chapter 4, which is the electrical chemistry, and now I have a couple of slides. They have like examples or a question to be accurate. So I want you to solve these questions. Okay, there are four questions only, and send me the answers by tomorrow. All right. This is the first slide, which has two questions, and the second one has also two questions. All right. Thank you so much.